So in this video, we're going to introduce the time series forecasting. Um, it's one of the models we're going to use is called Arima, auto-regression integrated moving average model. So this is one of the statistics models. It actually has majorly two components. One is the AR part, which is auto-regression, and the other one is actually MA. MA part is the moving average model, and this one is kind of combined the two together. It's called the ARIMA. So there is a lot of reading about the ARMA. Then the reference is actually from an article from the machinelearningplus.com, and feel free to read through. But I will just keep it short. And the basic ARIMA model is actually has two components. One is a P. The second one is Q. P is for the AR term, auto-regression. MA is a moving average term, so Q is for a moving average. And the D is actually the number of difference requiring to make the time series stationary, to make the data stationary. What does this mean? What is the difference? What is the station? The data normally are not, most of the data are not stationary. The so-called stationary means the probability density function of the data does not change according to time. So it will stay there like a white noise. So when we actually do the prediction, we have the conditional probability. So the condition, the base condition, the base probability will not change with time. So also the whole training, it's gonna be kind of converge. If it's not changing with the time, and most of the data are not stationary, so that's why we gotta find the number of differencing. A lot of times we need to do a first order of difference, so which means you're gonna take one value and subtract another value. So that's called the first order of difference. Sometimes even the first order difference is not enough. Then you have to take the difference on the difference. So that's actually take the one difference value and subtract another difference value. So that what becomes the second order of difference. So that's how do we do the number of differencing. So a lot of times one or two will do. If the data is stationary, then it's going to be 0. And so then what does the PDQ in ARIMA model mean? So its first step is you're going to check if the time series is stationary. And then you can check all of those, and there actually are packages helps us to calculate that. The way I understand is you don't need to understand in every detail about the model itself. You can think it as a black box. So when you pass the stationary data and you give the correct parameters, then you are going to get the training or predictive value. So that's just like the functions that we are using. So a lot of times you don't have to know the details of the implementation of a function. All you need to know is if you pass the correct parameters, it's going to give you the correct results. So that's how we're going to do this one. So we will directly jump to how do we use it instead of going through all those details. Because we're not a statistic or math major. So here is import. How do we import? We first import NumPy and pandas as PD, and we import one of the package called the AD folder. AD folder. It's actually ADF. ADF is one of the augmented decay folder testing. So this is like the statistic models that help us to determine if this data is stationary. Basically, there are two tests. We're going to mostly check the piece value. If the piece value is significantly less than, especially 0.05, then we will see, and there should have another condition. It's like the statistic value is less than the 1%, to 5%, 10% of critical values. Then we will announce that this data is actually already a stationary. If it's not stationary, then we're going to take the difference, the first order difference, and then apply it to this. If it becomes stationary, then we call this data. The original data was semi-stationary. Same thing you can apply to the second order of this second order of difference. If they're stationary, then you still can call it a semi-stationary. So this is basically show us that we read some data from the value from the www usage, the CSV. It's basically CSV file, and with the value and the dates. So we get the two values by calling the AD folder, so we can get the results. That's how we calculate it. And since this is not stationary, then we can actually get the the first order and the second order of difference. How do we do that? We first get all those values, right? We get the fig and the axis, and the axis. Then we can plot them. This is the subplot. This is original series. We can plot the original DF value, and then that's the axis, because we have like 3 rows, 2 columns. So we have the first figure is actually the actual value, the original value. Then we take the first order of difference, but simply just use the value dot diff. So that will give us the first order of differencing, and we can drop the null values, drop NA, drop null values. That will be the values, so we can plot it. And you can tell this is apparently the original data is not stationary. So and you can tell this is kind of like you can see a clear trend. It's going up. So this is not stationary. When we look at the first order of differencing, you see this is kind of like white noise. That means it's not changing its value according to the time. So this becomes somehow like semi-stationary. So this is stationary. And if you take the second order of the differencing by just to take the difference out of and not of the difference, difference of the difference. So that's what you do. And then that you get the second order of differencing. Then you can plot the difference of difference and drop the null value. So that will be this one. Apparently this one is look like a stationary too, because you don't see the pattern, you don't see the trend and the combination of those two. So look like it is stationary. But when you look at this one, first order and second order, look like this second order is kind of like processing, overdue. So it's a bit too much. So the first order should be good enough. So then we can actually start to apply the NDFs. So we can check if they're perfectly stationary. So doing the same thing, we load the data, we get the value as y, then we can test different models for the stationary. We can use ADF model, we can use KPSS, we can use PP. All of them are just those ones that we'll use as to test if they're stationary. Very likely you're going to run into some problems saying there's no module for this one. Then you're going to install by use pip install this package, and then you run it again, or you can use this pip install this one. It's then you run it again. Very likely it's going to give you the results. So I'm going to copy here, and then after installation we can run it again. So after installation we can run it again. So it's going to take a little while to calculate all those values. So let's take a look, and so the results actually will be 202. Okay, and then since we know that the first order of the DF is going to be the stationary, but what if I directly use the DF that's value, and then I directly apply to Arima? What will be the results? I will get the model, and then I use the model to fit, and the fit means the training. So we're going to use that value as a trained model, and then we get the summary of this model, and you will find this model is kind of it's okay. You have the standard error. It's something like this. It's not significant big, and so that's basically you can use it. And remember earlier when we use Arima, here the order I'm changing is like this is the number 2 is means the second order of difference, and it's giving us this. But when we use the first order, because earlier we said that the first order is good enough, and when you use the first order of the model Arima, you use the value and the order will be 111, and then when you do the model fit means the training, and then here's the results. You will notice that the standard error and everything seems a little bit better. So that means the second order of difference actually is kind of like overdo. It's overkill, so it's too much. So sometimes when you do too much, it's as bad as you don't do anything. So you got to do just do it right. So the first order is going to be better, and then you can actually plot the residual errors by just to get the DF data frame and use the model fit that the residual. It's going to give you all the residuals, and then you can plot. Again, in this one is 1/2, so I have 2 figures in one row, and so one of them is a residual, the other one is the density function. You see it's nicely, it's like a normal distribution, right? The actual value versus the fit. So when we are using the model.fit, and then we plot the prediction, so you can see it's very, very well matched with the actual value. So the forecasting value is in blue, and then the purple color is actually real values. And we can actually also do some prediction. We can has the ACF, and then here we can have the train and the test. Then we can actually put those training data, and then we train it right here. This step is actually we train the data, and then we get the trained data, and then now we can do the forecasting, means the prediction, with 95% confidence, and then you can get all those results, and then we can start to plot the results and show the results. And before we do that, we gotta make pandas series have lower, upper, and the actual results, forecasted results. So when we plot them together, you're gonna see these results. So you have forecast, actual value, and training value. So that's the training stop right here, and then you can start to predict. The actual will be right here, and we forecast right here. So that would be the results. And same thing here. We can actually train with the different water, and so sometimes when we go very weird some orders, then you get different results, and then you can see how much accuracy we can get by using the forecasting accuracy. Here is the forecast, here is accuracy, and we're going to calculate what's the mean, what's the maxima error, what's the all kinds of the results, and that's part of the statistics. We can see how accurate it is.